horizontal disk is oscillating in its own plane horizontally. This is a disk oscillating this way. With amplitude A and time period t, amplitude A and time period t. A body is placed on the disk and is about to slip on it. This is a body, let's say, of mass m placed on the disk. So this body will also execute SHM, right? And is about to slip on it. We need to find the coefficient of friction. Sound Ashina? Hello, hello, hello. Yeah. So this body is about to slip on it. Now one thing that if this platform has an amplitude A and time period t, then this mass m would have the same amplitude and the same time period of oscillation, right? At any point of time, suppose this was the mean position. This was the mean position of oscillation, and at this point the mass m is at x0, it's going to, what force does it require at x0? Kx. Kx is the force that it requires at x0, right? Kx directed towards O. Now, who provides this force? It's friction that's responsible to provide this force, right? So friction, and what would be the nature of this friction between small m and capital M? Static, because there is no actual relative motion between small m and the platform. The, the nature of friction is static. So then, in any case, F, frictional force must provide for this, Kx. Frictional force must provide for this, which is Kx. But there is a limit on F. What's the limit on the frictional force? It's always less than or equal to mu mg. It's always less than or equal to mu mg, frictional force, right? Static friction. So we have x less than or equal to mu mg by k. That means the maximum permissible value of x is mu mg by k, and the maximum permissible value of x is the amplitude of motion. So this must be equal to, let's say as a limiting case, equal to the amplitude of motion, and this will provide you the value of mu, the coefficient of friction, where evidently omega squared is k by m, omega is root k by m, and so this k by m can be written as omega squared, this k by m can be written as omega squared from here, and the time period is going to be 2 pi by omega. Time period is going to be 2 pi by omega. So t is known to us, omega can be written as 2 pi by t, and so on and so forth, right? Can do. Is it clear? Two particles are in SHM with the same amplitude and frequency along the same line and about the same point. If the maximum separation between them is root 3 times the amplitude, what is the phase difference between them? Let's say one particle executes SHM as x1 is a sine omega t, and let's say the other one is a sine omega t plus phi, where phi is the phase difference between the two oscillations. Alright. So at any given instant of time, the displacement of one particle is given by x1 equal to this, and at the same instant of time, the displacement of the other particle is given by x2 equal to this. So the separation between the two particles is going to be x2 minus x1, right? So delta x, the separation between the two particles is like a x2 minus x1, which is like A sine omega t plus phi minus sine omega t. So now we have like a sine c minus sine d, which is 2 sine c minus d by 2 cos c plus d by 2. Yes or no? 2 sine c minus d by 2 cos c plus d by 2, right? Which is 2a sine phi by 2 into cos omega t plus phi by 2, only cosmetic here. And what's given in the problem is that the maximum value of this is root 3 times a. What's given is that the maximum value of this expression is root 3 times a. Now, what's the maximum value of this expression? 2a sine phi by 2. Because the maximum value of, see, what's the variable here? This is the variable. At different t's, this number is varying, right? But what's the largest value of this number? 1. So the largest value of this expression is 2a sine phi by 2. 2a sine phi by 2, which means 2a sine phi by 2, that's given in the problem to be equal to root 3 times the amplitude. Root 3 times the amplitude. Phi by 2 is root 3 is sine phi by 2 is root 3 by 2, and so on and so forth. Phi by 2 must be 60 degrees or phi must be 120 degrees. So phi is 2 pi by 3. Phi is 2 pi by 3. Clear? So we have in problem 5 an endless chord comprising 2 chords of length 2L. See, this is L, one chord, and another chord of length 2L prime, and the mass per unit lengths, the mass per unit length of this is M, the mass per unit length of this is M prime. It's given that M prime greater than M. What's the period of, when slightly disturbed, it executes SHM. What's the period of SHM? What's the period of SHM? Now, see, if it was a uniform string like this, and you disturbed it by a small amount x, you pulled it down by a small amount x, what would happen? Nothing would happen. Why? Because the weight on this side would have been the same as the weight on this side. There would be no change brought about, right? Suppose this part was heavier compared to this part, then it will move like this. If this was heavier compared to this, it will move this way. Yes or no? Huh? Now, given this basic understanding, realize that we have a setup of this kind, all right, and we initiate a small displacement in the sense I initiate the following. I pull this down by an amount x. I pull this interface down by an amount x. If I pull this down by an amount x, this becomes L plus x, this becomes L prime minus x, this becomes L prime plus x, L minus x, right? That's what happens. So in the new state, having disturbed it x units downwards, let's say, I have the following. So then I have like a L plus X, L prime minus X, L prime plus X, and L minus X, right? Now it's given that this shaded portion has a greater mass per unit length compared to this. This L prime has a greater mass per unit length compared to this. Now, if I shifted this down, then the composition of the right hand side is different from the composition of the left hand side. The right hand side now has a greater variety of the smaller mass per unit length and a smaller variety of the greater mass per unit length. On the left hand side, it's just the other way around. I have a smaller variety, a smaller proportion of the smaller mass per unit length and a greater proportion of the greater mass per unit length. So obviously you would expect this portion to be heavier than this portion to be heavier than this portion, and if this portion, the portion on the left hand side is heavier compared to the portion on the right hand side, the thing would have a tendency to move like this, right? The thing would have a tendency to move this way, and the force that this experiences would be difference in the two weights, difference in this weight minus this weight. The restoring force would be this weight minus this weight would be the restoring force, right? This weight minus this weight would be the restoring force. So having displaced it x units as shown, the restoring force is going to be difference in the two weights. Difference in the two weights is the restoring force. Which is like weight on this side, which is m into L minus x plus m prime into L prime plus x minus m into L plus x minus m, or rather plus m prime into L prime minus x into G. That's our restoring force, which is m into minus 2x, see, this m into minus 2x plus m prime into 2x G, which is like of m prime minus m to m prime into to G into x. Hey, restoring force proportional to the displacement x. This must be the constant of proportionality. 2 into this must be the constant of proportionality. Motion executed must be simple harmonic. So the k of the motion is this. The k of the motion is 2m prime minus m into G. That's the k of the motion. The mass would be the total mass of the system. Total mass of the system is capital M would be m into 2l plus m prime into 2l prime. That's the total mass. So the omega of the motion is going to be root k divided by capital M. Root k divided by capital M. That's the omega of the motion. Time period is going to be 2 pi by omega, etc. Sounds all right? Okay, we have a simple pendulum here. M is the mass of the bob, is immersed in a liquid. Density of the material of the bob is rho, and the liquid has density rho by n. The liquid has density rho by n. We need to find the time period. Well, if it was an air, the time period would have been 2 pi root L by G. It would have been 2 pi root L by G, because in air, it's mg, and the G effective is equal to G. G effective is equal to G. All right. But suppose you had to push it up. Along with mg downwards, if you had to push it up, then the net force downwards will not be mg. It would be mg minus the upward force. So the G effective would become less than G. G effective would become less than G, right? So in this case, realize that the liquid body is exerting an upthrust. As a result, the net downward force is mg minus upthrust. So the G effective becomes less than G. How does one find G effective? Okay, mg minus upthrust. Upthrust is weight of liquid displaced. What's the volume of liquid displaced? Volume of liquid displaced would be the volume of the bop. So m by rho is the volume of the bop into, so this is the volume of the liquid displaced, into density of the liquid, which is rho by n, into G. That's the weight of the liquid displaced. That's the weight of the liquid displaced. So this is, let's say, effectively m into G effective. The G effective for the system can be given by this. So the left hand side becomes mg into 1 minus 1 by n. That's m G effective. So you would then want to perceive G effective for the pendulum as G into 1 minus 1 by n. G into 1 minus 1 by n is the equivalent G for the pendulum immersed in a liquid. The time period then would be 2 pi root L divided by G effective. Time period is going to be 2 pi root L divided by G effective. Okay. There is a block of mass m and another connected to a spring resting on a frictionless surface, and they undergo collision, and the nature of collision is given to be inelastic. Although you know there is a space between in and elastic, that's a typo there. So that's an inelastic collision. Inelastic collision means what? They stick together. E is 0, that means after the collision they move together as one unit. It also implies that there is loss of energy. Inelastic collision also implies that there is loss of kinetic energy. So in the event of an inelastic collision, what's the conservation law that would be applicable? Momentum conservation, not kinetic energy. Kinetic energy before collision and after collision would be different. There is loss of kinetic energy in an inelastic collision, but momentum remains preserved. Momentum does remain preserved. So then after collision, this becomes like a 2m, and they move together with a common velocity vc. So the total momentum of this m and this m before collision is m into v. Yes, m into v. And that must be equal to total momentum just after collision, which is 2m into vc. Vc then becomes equal to v by 2. Vc then becomes equal to v by 2. Now realize that at this point of time the spring was in its relaxed state, so it was not exerting any force, external force, and therefore preserving linear momentum was a viable proposition here. Okay. So then, just after collision, what's the quantum of total energy that the system houses? What's the total energy that the system houses? Half of 2m into Vc squared. Vc means V by 2 whole square. Now the spring begins to compress, hogging up kinetic energy. So the spring gets more and more compressed. The kinetic energy continues to dip. Eventually, in the state of maximum compression of the spring, all the kinetic energy would surface as elastic potential energy in the spring. That is in the amplitude position. That means all of this will appear as half k a square, in the state of maximum compression of the spring, that means in the amplitude position. And then this will give you access to the amplitude, of motion. How about it? Sounds okay? A block is resting on a piston which is moving vertically in SHM with a period of 1 second. At a particular amplitude of this motion, the block and the piston will separate. What is the maximum velocity of the piston at this amplitude? Okay. Now, remember I had a discussion that was dedicated to this vertical oscillation, and I told you that the maximum displacement A would always be less than or equal to g by omega squared for the block to not separate with its mother platform. This was a result that I had served to you as a ready reckoner. Remember this? A should not exceed g by omega squared. Either you can play with omega or you can play with A. No, you can't play with g. You can either play with A or you can play with omega. For whatever combinations of A and omega that you are seeking, A should always be less than or equal to g by omega squared, right? That means the maximum amplitude is g by omega squared for the separation not to take place. In this case, you don't have an option of playing with omega because time period is given to be 1 second. So omega is 2 pi by time period. So omega is known. So A max is g by 2 pi whole square. Actually, as an approximation, pi square is approximately equal to g. So this will become approximately 0.25. But in any case, that's not important. The maximum velocity for this amplitude would be omega A. The maximum velocity for this amplitude is going to be omega times A. That's the maximum velocity for this amplitude, omega times A. Omega is known to us, etc. A particle is subject simultaneously to 3 SHMs of equal amplitudes. A, which is, let's say, the zero phase. The phase of the second motion is ahead of the first, is ahead by 60 degrees. And the phase of the third motion is 60 degrees ahead of the second. Third motion, 60 degrees ahead of the second, means this also is 60 degrees. This is 120 degrees, so this is also 60 degrees. So the net A from these 3 vectors would give you the amplitude of the resulting motion. That's what I proved in the class for you, right? So all that you need to do is you need to vectorially add these 3 phases. Let's say this is x, this is y. The x component of the resultant of these A's is going to be A plus A cos 60 degrees minus A cos 60 degrees, which is A, and the y component of the resultant of these A's is going to be 2A sin 60 degrees. And the effective A is going to be root ax squared plus ay squared. Ax squared plus ay squared would be the effective A. Right? And the phase of the resulting motion is going to be, see, we found this effective A, which is the resultant of ax and ay. This is the zero phase line. Then this angle theta would tell us the phase. So tan theta would be ay by ax. tan theta would be AY by AX. Such would be theta. Problem 13. Shall I wipe this off? A spring of force constant 200 Newton per meter is mounted as shown, and a mass 2 kg is attached to the free end. If the system is given an initial displacement of 0.05 meters and an initial velocity of 2 meters per second, find the amplitude of motion. So what we do here is, there is a spring of force constant K. It's elongated by a certain amount. This is the natural length of the spring. It's elongated by an amount x equal to 0.05 meters. And it's not just elongated. At this instant, this is also provided a velocity of 2 meters per second. We need to find the amplitude of the simple harmonic motion. Okay, now what's the total energy that you are supplying to the system? Half kx squared plus half mv squared. That's the total energy that you're supplying to the system at any point of time. This is the total energy that's delegated between elastic potential energy and kinetic energy, right? At the amplitude position, this entire energy gets translated into elastic potential energy, right? That means if A is the amplitude, then at the amplitude position, this must be equal to half k a squared. That's what you do. All right. 20, a body moving along the straight line OAB. This is O, and I never said O is the mean position. O is just the origin of coordinates. AB with zero velocities at A and B means A and B must be the extreme positions for the oscillation, and velocity V when halfway between them is M, and velocity V. If the coordinates with A and B with O as the origin are small a and small b, that means this is A0, this is B0, it's oscillating between these two limits, A and B. That means the length AB is B minus A. The amplitude A would be half of this. That means B minus A by 2 is the amplitude, right? And the velocity at the mean position V must be omega A. V must be omega times amplitude, omega times B minus A by 2. So omega is known as 2V by B minus A. And if omega is known, then time period is 2 pi by omega, etc. That's it. Sorry? Acha, suno. Other side hone se bhi distance between 2 points whose coordinates are these will still be B minus A. तो A कोई बात नहीं, क्या फर्क पड़ता? तब suppose it was on the other side of the origin, it still has coordinates B comma 0, right? If there are 2 points with coordinates A0 and B0, irrespective, उनका sign तो उसके अंदर ही है, so what's the separation between them? Will still be B minus A, है ना? A and B are 2 points at which its velocity is 0. Extreme positions, therefore. It passes through a certain point P at an interval of half a second and 3/2 seconds with a speed of 3 meters per second. Determine the maximum speed of the particle. These are the extreme positions A and B. This is the auxiliary circle. So if omega is the angular frequency of oscillation of this, then the auxiliary particle moves with an angular speed omega, right? Uniform angular speed omega. I gave you this auxiliary circle frequency, right? And then there is a point P. The velocity of the point P is given to be 3 meters per second. Is given to be 3 meters per second. P is a certain point P. Is a certain point along AB. Now it passes this point P. It passes this point P at intervals of half a second and 3/2 seconds. Why half a second? Okay. When it was at P, it could be heading in this direction or it could be heading in this direction. Half a second because the following happens. It goes from P to B and then it goes from B to P. That's half a second. That's half a second. Right? P to B and then back to P. That's half a second? No? And time for PB must be equal to time for BP. Each must be 1/4 of a second. You've seen that? And then next what happens is, it starts moving in this direction and then it goes from P to A and then A to P. This takes 3/2 seconds. This takes 3/2 seconds. That means PA must be equal to AP must be 3/4 seconds. Right? Now one thing for sure, that this time P to B, B to P half a second, and then to A and back to P 3/2 seconds. That means what's the time period of motion? 3/2 plus half, 2 seconds is the time period of motion. Do you realize that? This and then back to P with the same kinematic status. That's 3/2 plus 3/2 seconds. That is 2 seconds. That's the time period of motion. That's a full oscillation in the process. Each point between A and B would be covered exactly twice. Right? So the time period of motion is half plus 3/2, which is 2 seconds is the time period of motion. Right? Now, let's locate the point P. Let's locate the point P. You might just want to draw a fresh figure for your sake. On the board I can do this. Now what's the time taken from P to B? 1/4 of a second? 1/4 of a second, right? Because this whole thing is half a second. So one-way trip would be 1/4 of a second, right? Now, or in other words, this is the mean position O. From B to P, what's the time taken? 1/4 of a second. So by the time the oscillator goes from B to P, by the time the oscillator goes from B to P, the auxiliary particle goes from B to P prime. The auxiliary particle goes from B to P prime. Yes or no? That means to go from B to P prime, what's the time taken by the auxiliary particle? 1/4 of a second, because that's the time taken by the oscillator to go from B to P. So 1/4 of a second to go from B to P prime, right? 1/4 of a second. So then this time is 1/4 of a second. Now in 1/4 of a second with an angular speed omega, what's the angle that it's going to describe at the center of the circle? What's the angle theta that it's going to describe at the center of the circle? Omega t? Omega t, this particle with uniform circular motion would describe an angle theta equal to omega times t. Omega times t means omega is known to us. Why? Because omega is 2 pi by t. That is pi radians per second is omega. So theta is omega t. Omega is pi into t, 1/4. So this angle is known to be a 45 degrees. This angle is 45 degrees. Now, if A is this amplitude, the radius of the circle would be the amplitude of motion, right? Then what would OP be? A cos theta. OP would be A cos theta, that is A cos 45 degrees. That means A by root 2 would be OP. A by root 2 would be OP. Right? So what's X for P? A by root 2. X for P is A by root 2. And we know this result. V equals omega root A squared minus X squared, speed at any given X. Speed at any given X is known to us. V at P is given to be 3 meters per second. Omega at P is, or omega, sorry, for the motion is pi radians per second. Root A squared minus X squared. X for P is A by root 2. So A squared by 2. Right. So this is pi A by root 2. So A is known to us. A would be 3 root 2 by pi. A would be, amplitude of motion is going to be 3 root 2 by pi, right? What's sought in the problem is the maximum speed for the oscillator. The maximum speed for the oscillator occurs at the mean position. So the maximum speed for the oscillator would be omega times A. Omega times A. Omega means pi times A, which is 3 root 2 by pi. This is the maximum speed for the oscillator. Got me? Alright, so there was a spring in its natural state with a mass m1 attached at one end, right? And then m2 was pushed against m1. m2 was pushed against m1 by an amount d. So that the spring got deformed by an amount d. The spring got deformed by an amount d. Okay. Now, once the spring got deformed by an amount d, this is like m1 and m2. The spring has got deformed by an amount d. The energy stored in the spring is half kd squared, Okay. And now the spring would begin to unfold. It would open up. So when it opens up, it pushes the M1, M2 combo rightwards towards the mean position. It pushes M1 and M2 towards the mean position. Eventually, when M1 and M2 arrive at the mean position, the spring has been up from this point to this point. The spring has been pushing M1 and M2, and they move together, right? Once they reach this mean position, the physics changes a little bit. The spring is in its natural state, but the masses m1 and m2 would have developed a certain velocity v rightwards. How would you know what that velocity is? Well, after all, half kd squared must have been half m1 plus m2 v squared, right? No energy has been lost in the process. Must have happened this way. Now, at the mean position, just slightly beyond this mean position, the spring stretches out. From this point, let's say just slightly to the right, the spring would have got slightly elongated. Now, if the spring just slightly beyond the mean position gets slightly elongated, the spring is communicating only with M1. So what the spring does is, it holds back M1. It tries to pull M1 back, but M1 still moves because of inertia, right? But there is a retardation on M1. There is a retardation on M1 which is not experienced by M2. Which is not experienced by M2. So then, slightly beyond the mean position, M1 under the influence of the spring retards and M2 moves away with a velocity v. M2 moves away with a velocity v. So then, slightly beyond the mean position, M2 goes out of picture. Right? Yes or no? So then, it's only M1 which stays put. It's only M1 that stays put. And the spring energy is half kd squared. The spring energy is half kd squared. Just slightly beyond the mean position, it's still half kd squared, which has got converted into half m1 v squared, which gets converted into half m1 v squared. See, the energy of the mass m1 is half m1 v squared. V squared is given by this, and eventually the spring elongates to a maximum value a, where this half m1 v squared would appear as half ka squared, right? Of this total energy, half m2 v squared gets decoupled from the system. The energy that stays in the system is half m1 v squared, and this half m1 v squared gets converted into the new amplitude of motion, right? And then to obtain, so I can say this by this is this by this and solve for amplitude. See, this by this is this by this. I can solve for the amplitude of motion. How about this? Is that okay? You know what I'm saying? I hope you realize why M2 would move away from this synergy. Because the spring is pulling M1 back, and therefore this M1 begins to get retarded, whereas M2 doesn't get retarded. It just walks away with the energy half M2 v squared. You know what I'm saying? So then the only energy that stays in the system is half m1 v squared. In the amplitude position, it appears as half ka squared. So then just divide this by this to obtain the value of the amplitude, new amplitude. Sounds all right?